In this session, we're going to discuss primes and greatest common divisors. So under this session, okay, we're going to discuss specifically prime numbers and their properties, conjectures and open problems about primes, greatest common divisor or GCD, and least common multiple or LCM, the Euclidean algorithm to determine the GCD, and GCD as linear combination. Okay, so let's define first what is a prime number. So based on our book, it is a positive integer p greater than 1 is called prime if the only positive factors of p are 1 and p. So it means itself and 1 should be the only factor of that given number. Okay, so that it could be considered as a prime number. Okay, and it should be greater than 1. Okay, so 1 is not a prime number because again, based on the if statement, p and 1. Okay, it means we have two distinct values. Okay, itself and 1. 1 is just one value. Okay, when we get the factor of it. Okay, so that's why 1 is not considered as a prime number. Okay, prime number should be greater than 1, and the factors are itself and 1. And in case if it's not a prime number, it is called composite. If say composite, it has more than two factors. Okay, we have two values, more than two values. Okay, as factor of a given number. Okay, so for example, 7. 7 is a prime number. Okay, because its factor is just 1 and 7. But for 9, it's not. It's a composite number. Why? Aside from 1 and 9 as a factor, 3 is also a factor of 9 since it is divisible by 3. Okay, so we have 3 factors for 9. So therefore, it's a composite number. Okay, and we also have a theorem that involves a prime number. Okay, so it's stated that every positive integer greater than 1 can be written uniquely as a prime or as the product of two or more primes where the prime factors are written in order of non-decreasing size. So if we have a given number, we could rewrite it based on the prime factors. Okay, and those prime factors should be non-decreasing size. So we start from the smallest up to the biggest prime number. Okay, so when we multiply this prime number, will give us the given number. So for example, 100. So what are the prime number that we need to multiply to get 100? Okay, so the numbers are 2. Okay, so 2 will be multiplied by 2, multiplied by 5, and multiplied by 5. Okay, so 2 times 2 is 4, 4 times 5 is 20, times 5 it's 100. And 2 and 5 are prime numbers. And we could rewrite this as 2 squared, 5 squared. This is called the prime factors of 100. Okay, how about 641? Since this is a prime number, automatically prime factor is 641. Okay, we don't need to write the times 1. Okay, because it's given. Okay, and then for 999, so we need to multiply 3 by 3 by 3 and by 37 to get 999, or in short, 3 cubed times 37. And for 1024, so 2 times 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 2, or 2 raised to 10 to get 1024. Okay, so again, we could rewrite a given positive integer, which is greater than 1, okay, by using prime factors, by using its prime factors. Okay, so this is the theorem. Okay, this is the theorem. Okay, so later we're going to use this theorem to determine the GCD and LCM. Okay, And in case you want to determine the different prime numbers in a given set, so for example, 1 to 100, we want to determine the different prime numbers between these two values. Okay, so we could apply the concept or the algorithm given or introduced by Eratosthenes. Okay, Eratosthenes. So, so he's a mathematician. Okay, so this is how we determine the prime number between two given values. Okay, so for example, between 1 and 100. So since 1 is not a prime number, so we're going to remove it from the given set to determine the prime numbers. Okay, so write everything. So the first step will be delete all the integers other than 2 divisible by 2. So it means remove all divisible by 2 but retain 2. So it means remove 4, 6, 8, 10, 12, 15, 12, 16, 18, 20 in our list. Okay. And then after removing all divisible by 2, we go to removing divisible by 3. But don't forget, retain the value 3. Okay. So you're just going to remove the other divisible by 3 aside from 3. Okay. So what will be the next prime number after 3? It's 5. So all divisible by 5 except for 5, remove it from the list. Okay, and then next prime number is 7. So it means remove all divisible by 7 except for 7 on the list. Okay, so we have a pattern now. Am I right? So we're going to determine the next prime number and remove all values or numbers which is divisible by it. Okay, remove it. And then after removing, you go to the next prime number and then repeat it. Repeat the removal of the divisible values. Okay, until we get the highest prime number of the given set. Okay, so that's the sieve of Eratosthenes. Okay, or the basically getting the prime number from a given set. So this is just a graphical representation of how we do it. Okay, so we have the list. Remove all divisible by 2, remove all divisible by 3, divisible by 5, divisible by 7. But don't forget, retain 2, 3, 5, and 7, okay, on the list. Okay, so that's the sieve of Eratosthenes. And also, our favorite mathematician, which is Euclid, okay, so he stated that he stated that there are infinitely many primes. Okay, so this was proven by contradiction, and based on that, so we could say that this theorem is correct. Okay, so I'm not going to prove it anymore, but just tanggapin na lang natin. Okay, since it's already been proven. Okay, and we also have Mersenne primes. So what is the Mersenne prime? We have a formula that defines the Mersenne prime. Okay, so prime numbers of the form 2 raised to p minus 1, where p is prime, are called Mersenne prime. So the result of this equation should be a prime number. Okay, so when we substitute any prime number to our equation, the result should be a prime number. So to be considered as Mersenne primes. So for example, okay, so we're going to substitute 2, which is a prime number. So 2 squared minus 1, result 3. 3 is a prime number, so therefore this is a Mersenne prime. So next, 3. So 2 cubed minus 1, the result is 7. 7 is a prime number, so it's a Mersenne prime. So next, 2 raised to 5 minus 1, okay? So 2 raised to 5 is 32 minus 1, 31. 31 is a prime number, so it's a Mersenne prime. 7 is again a prime number, so 2 raised to 7 minus 1 is 127. So it's a Mersenne prime. Okay, as long as again, when we substitute a prime number to this to the equation 2 raised to p minus 1, and then the result is a prime number, it is considered as a Mersenne prime. Okay? But there are instances, even though we substitute p, okay, prime number to p, it will give us a composite number. So for example, when we substitute 11 to our equation, 2 raised to 11 minus 1 is 2047, which is not a prime number since we have other factor aside from 1 times 1 and 2047. So we have 23 and 89 to yield 2047. So therefore, the result is not a prime number. Therefore, this is not a Mersenne prime number. Again, to define Mersenne prime, substitute p should be prime, and when we substitute it to our equation, it should also be a prime number. The result should be a prime number to be considered as Mersenne prime. Okay, so based on their study, the highest known Mersenne prime number is this. Okay, 2 raised to 43,112,609 minus 1. Okay, so this is the known Mersenne prime. So basically, they created a special computer just to determine the highest Mersenne prime number. Okay, so why do we need to determine the prime numbers? Because we could use it in cryptography. Okay, so cryptography is hiding details in a file, okay, or added security to our file, okay, or representing an ordinary file, remodeling a certain file, okay, to a new one, okay, before we send it. That's cryptography, okay. So we could use prime number for that. One application of prime number, okay. And some conjectures about primes. So we have Goldbach conjecture. So every even integers n greater than 2 is the sum of two primes. So for example, sum of two primes, 4, 3 plus 1, but 1 is not a prime. So exclude that. Okay, let's have 5, 3 and 2, 7. Okay, 7 is not even. So X ulit. So it should be 8. What is 8? 5 and 3. Okay, 11. It's not even. Ano ba nangyari sa akin? 12 pala. 5 and 7. Okay, 14. 7 and 7. Okay, so we have two prime numbers. When we add, it will give us an even integer. Okay, that's Goldbach conjecture. Okay, another conjecture, there are infinitely many primes of the form n squared plus 1, where n is a positive integer. Definitely, when you substitute a value and we add 1, it's a prime number. Okay, so for example, n is 1. 1 squared plus 1 is 2. It's a prime number. 2 squared plus 1, 5. It's a prime number. Okay, 3 squared plus 1, it's not a prime, so it's not part of this. How about 5 squared? No, it's 26. But there are lots of prime number that follows this equation, n squared plus 1, but not all. Okay, there are lots. Okay, and also we have a conjecture that we call the twin prime conjecture. There are infinitely many pairs of twin primes. Okay, so what do you mean by twin primes? Twin primes are a pair of primes that differ by 2. Okay, for example, 3 and 5, 5 and 7, 11 and 13. So the only difference between these two primes is 2. Okay, so that's the twin prime conjecture. Okay, so again, we have Goldbach conjecture. we have the twin prime conjecture, and lots of rhymes follows the form n squared plus 1. Okay, now let's move on with greatest common divisor. So let's define it first. So let a and b integers, not both 0. Okay, the largest integer d such that d divides a and also d divides b is called the greatest common divisor of a and b. The greatest common divisor of a and b is denoted by GCDAB. Again, we have a divisor. Okay, this is, it could divide a two number, so which are a and b. Okay, and this divisor is the highest divisor wherein it yield. Okay, when we divide it to a and b, it yield an integer. Okay, so that is GCD, or greatest common divisor. Okay, so among the prime, among the among the factors, okay, the highest factor that we could divide to a and b, okay, that yields an integer is considered as GCD. Okay, so for example, what is the greatest common divisor of 24 and 36? Okay, so we could list all the factors of 24 and 36. Okay, and then kung ano yung which is common to 24 and 36. So let's define it, and then which is the highest, that will be the GCD. Okay, so which is 12. So for 24, we have 24 and 1, 12 and 2, okay, 6 and 4, 3 and 8. Am I right? Okay, and then for 36, 3 times 12, 6 times 6, 4 times 9, etc., etc. And the highest common between 24 and 36 as their factor, it's 12. Okay, and for 17 and 22, 17 is a prime number, so 1 and 17. 22 is not divisible by 17. Okay, so therefore, the greatest common divisor, okay, is 1. Okay, so the only common between 17 and 22 is 1. So that's why the GCD is 1. Okay, so again, greatest common divisor, the integers a and b are relative prime if their greatest common divisor is 1. Okay, relative prime if their common divisor is 1. So 17 and 22 is considered as relative prime because the only factor that they add which is common between these two values is 1. Okay, so this is considered as relative prime. Okay, so let's consider this example. Determine whether the integers 10, 17, and 21 are pairwise relative prime. So if say pairwise relative prime, so all of them, okay, when we pair, okay, 10, 17, 10, 21, 17, 21, will yield a common divisor, greatest common divisor, which is 1. Okay, so we're going to pair the given 10, 17, 17, 21, 10, 21. Okay, so let's check for 10, 17, and 21. 10 and 17. Okay, 10 and 17, the greatest common divisor is 1. GCD for 10 and 21 because it's 2, 5, 1, 10. Okay, so 21. Okay, so the only common is 1. And for the pair between 17 and 21, okay, so we also have 1. Okay, so therefore, since all, when we pair all the given, the result is 1, the GCD result is 1, therefore it is considered as pairwise relative prime. Okay, And how about 10, 19, and 24? Okay, if one of the pair doesn't yield to 1 as its GCD, it is not considered as pairwise relative prime. It's not pairwise relative prime. So don't forget that. So, okay, so for 10 and 24, okay, so what is the greatest common factor? It's 2. Since it's not 1, automatically we don't need to test the other pair if the GCD is equal to 1. Okay, since the first the first pair fail. Okay, so therefore we don't need to proceed to the next next step of our solution, and we could conclude that 10, 19, and 24 are not pairwise relative prime due to GCD 1024 is 2. Okay, so it's not pairwise relative prime. Okay, now, so there are different ways to determine the GCD. Okay, so one way is using prime factorization. Okay, so still remember the first theory that we have discussed in this session. We could rewrite, wherein we could rewrite the given using prime factors. Okay, so for example, we have 120. So the prime factor of 120 is 2 cubed times 3 times 5. Okay, and for 500, we have 2 squared times 5 cubed. Okay, so to get the GCD, okay, we get all the prime factor of both, okay, of both given. So we have 2, 3, 5. So 2, 3, 5. Dito naman 2, 5. So it's present. Okay, so we're just going to combine all the prime factors of the given. So 2, 3, 5. And then we're going to get the minimum exponent of the prime factor from the given. Okay, for example, for 2. So we have exponent 3, exponent 2, which is the minimum 2. So we're going to get 2. Okay, so for our solution, get the minimum 2. How about 3? So this is 1. And since this is 3 is not present in 500, it means the exponent is 0 for 3. So it means 3 raised to 0 is 1. Okay, so that's why we have 3 here, but the exponent is 0. So therefore, 1 and 0 minimum is 0. So that's why we have 0 here. And then for 5, exponent of this 5 is 1. Here is 3. Between 1 and 3, the smallest is 1. So get 1. Okay, so these are the minimum exponent of the prime factor of the 2 given. Okay, 2 squared, 3, and 5 raised to 1. So after getting the minimum, okay, the prime factor with minimum exponent, okay, multiply it, and then the product is actually the greatest common divisor, so which is 20. Okay, so we have 2 squared times 3 times 5, 20. So this is the GCD of 120 and 500. Okay, so that's how we use prime factorization to determine GCD. So again, get the prime factor of the given. Okay, combine all the prime factor and then get the minimum exponent of the prime factor. Okay, after getting, multiply, okay, the prime factor with the minimum exponent, and then the result is the GCD of the given. Okay, so that will be our solution. How about least common multiple? Okay, say least common multiple. Okay, the least common multiple of the positive integers a and b is the smallest positive integer that is divisible by both a and b. Okay, so a and b is divisible. The given number is divisible both by a and b. So it means we could divide a to the given value, and it will yield an integer. Same as with b, when we divide it to by b, the result is an integer. Okay, so LCM, the smallest value wherein we could divide a and b and will yield an integer. That's LCM. Okay, so the solution for LCM is almost the same as in getting the GCD. But the only difference would be, instead of getting the minimum exponent, it will be the maximum exponent of the given. Okay? So that will be our solution. Okay, so for example, again, so this is the prime factor of a given number, 2 cubed, 3 raised to 5, 7 squared, and the second number is 2 to the 4, 3 cubed. Again, same as with GCD, get all the prime factors. So which are 2, 3, 7, 2, 3, 7. It's also present here, so it's just 2, 3, 7. And then get the maximum exponent of the prime numbers. Okay, between these two and these two. The highest exponent is 4. Get 4. How about sa 3, 5, and 3? Get 5 as your exponent. And for 7, so we have 2 here, but it's not present here. If it's not present, again, the exponent is 0. Okay, since we're getting the highest exponent, so we're going to get 2. Okay, so 2 raised to 4 times 3 raised to 5 times 7 raised to 2. Multiply this, and then that will be your LCM. Okay, so that will be your LCM. GCD, minimum exponent. LCM, maximum exponent. Okay, and also we have another theorem, which is theorem number 5. Okay, so that involves GCD and LCM. So let a and b be positive integer. So when we multiply a and b, so it is equal to GCD AB times LCM AB. Okay, so when we multiply the GCD and the LCM of AB, it will yield to the product of AB. Okay, so that's term number 5. And another way of determining our GCD is using Euclidean algorithm. Okay, so for Euclidean algorithm, so the Euclidean algorithm is an efficient method for computing the greatest common divisor of two integers. It is based on the idea that if A is greater than B and R is the remainder, when A is divided by B, then GCD AB is equal to GCD B, R. Okay, so basically we're going to use the division algorithm to determine the GCD. So for example, so we're going to get the GCD between 91 and 287. So we're going to divide 91 to 287, okay, using the division algorithm. So 287 is equal to 91, okay, and then how many 91 we need to get somehow to 87? So 3 plus the excess 14. Okay, and then next would be we're going to divide 91 by the excess. Okay, so it will be 91 is equal to 14 times 6 plus the excess, which is 7. And we're going to repeat what we have done. Okay, so now, so 14 will be your new B, and your new divisor is 7. Okay, So 14 is equal to 7 times 2 plus 0. Okay, so if the, what do you call this, the excess is equal to 0 or the remainder is equal to 0, we stop the division algorithm and we get, okay, the quotient, which is 7, okay, to, and then it will be your GCD. Okay, so that's it. So that's Euclidean algorithm. So from 287.91, it's equivalent to 91.14. Okay, and then GCD of 14 and 7 is equal to 7. Okay, so that's Euclidean algorithm. So again, the highest value will be the next B for our algorithm, for our division algorithm. So that's Euclidean. Okay, so that's it for this session. So if you have any question, kindly send me a message. So thank you for listening. Okay, so again, we discussed prime number, Euclidean algorithm, and other procedure in determining how to get the GCD and LCD, and some theorem that involves prime numbers. Okay, so thank you guys. So see you in the next video lecture. Thank you.